Good morning students. Today video is going to see magnetic effect of current. The magnetic effect of current, it was on 21st as April 1820. Hans Christian Oersted, a Danish physics was giving a lecture. He was demonstrating electrical circuits in that class. He had to often switch on and off the circuit during the lecture. Accidentally, he noticed the needle of the magnetic compass that was on the table. Okay, it deflected whenever he switched on. The current was flowing through the wire. The compass needle moved only slightly, so that the did not even notice. But it was clear to Oersted that something significant was happening. He conducted many experiments to find out the startlingly affect the magnetic effect of the current. The two types of no deflection when there is no current. The second one point, deflections when there is current. The two part of the current, the directions of the magnetic lines around a current carrying a conductor can be easily understood using the right hand thumb rule. Hold the wire with four finger of your right hand with thumbs positions. If the directions of the current is towards the thumb in the magnetic lines, curl in the some directions as your other four fingers, as this shown that the magnetic field is always perpendicular to the directions of current. The first one, see this picture. The first one, the strength of the magnetic field at a point due to current carrying wire depends on the first one point, current in the wire. The second one, distance of the point from the wire. The third one point, the orientations of the point from wire. The last one, the magnetic nature of the medium. The magnetic field lines are stronger near the current carrying wire and it diminished as you go away from it. This is represented by drawing magnetic field lines closer together near the wire and further away from the wire. Okay, the next one topic discuss force on a current carrying conductor in a magnetic field. The first one, magnetic field into page. H.A. Lawrence found that a change moving in a magnetic field in a directions other than the direction of magnetic field expressions a force. It is called the magnetic Lorentz force. What is meant by called the magnetic Lorentz force? The directions of magnetic field experience a force. It is called the magnetic Lorentz force. Since charge in motion institutes a current, a conductor carrying moving change place in magnetic field other than the directions of magnetic field will also experience a force and can produce motion in the conductor. See the picture. This activity we infer that a current carrying wire has a magnetic field perpendicular to the wire by looking at the deflections of the compass needle in the vicinity of a current carrying conductor. The deflections of the needle implies that the current carrying conductor extend a force on the compass needle. In 1821, Michael Faraday discovered that a current carrying conductor also get deflected when it in the place. A magnetic field can see the magnetic field of the paramagnet and the magnetic field produced by the current carrying conductor interact and produce a force on the conductor. The view perpendicular to the directions of current is shown this picture. Deflections of current carrying wire in the magnetic field. The current which leads to magnetic property here. Every obtaining electron in its orbit is like a current carrying lobe. Even though in all materials electrons orbit around the nucleus, only for certain special type of material called magnetic material. The motion of electrons around the nucleus gets added up, and as a result, we have paramagnetic field. See the picture. Force on a current carrying conductor, keep it in magnetic field. Okay, if a current I is the flowing through a conductor of length L keep it perpendicular to the magnetic field. So B, then the force F experienced by it is given by the equations F is equal to ILB. The above equation indicates that the force in proportional to current through the conductor, length of the conductor and the magnetic field in which the current carrying conductor is keep it. Okay, the first one, the force is the always vector quality. The force is the always is the vector quality. The first one, see the picture. See this picture. The force is always a vector quality. Vector quantity has both magnitude and direction. It means we should know the direction in which the force would act. The direction is often found using what is known as Fleming left hand rule. Left hand rule, formulated by the scientist John Ambrose Fleming. Okay, the law states that while stretching the three finger of left hand in perpendicular, the first one manner with each other, if the direction of the current is denoted by the middle finger of the left hand and the second finger is for the direction of the magnetic field, then the thumb of the left hand denoted the directions of the force or movement of the conductor. Okay, the first ones, the for example, the Fleming left hand rule. The Fleming left hand rule. The second one, forces on parallel current carrying conductors. The parallel current carrying conductors. The parallel current carrying conductors, attractive and repulsive force on current carrying wires. So we have see that current carrying conductor has magnetic field around it. If we place another conductor carrying current parallel to the first one, the second conductor will experience a force due to the magnetic field of the first conductor. Similarly, the first conductor will experience a force due to the magnetic field of the second conductor. These two forces will be equal in magnitude and opposite in direction. For example, the Fleming, using Fleming left hand rule, we can find that the direction of the force on each wire would be towards each other when the current in both of them are flowing in the same direction. That is, the wires would experience an attractive force. However, if the direction of the flow of current is in opposite direction, then the force on each of the wire will be in opposite direction. This is our shown in this picture. The perpendicular directions. The first one, the attractive forces and repulsive forces, they are shown in figure. The perpendicular view of the same is figures. The first one, connection between electricity and magnetism. The first, before 18th century, people thought that magnetism and electricity were separate subject of study. After Aristotle's experiment, the electricity and magnetism were united and becomes a single subject called electromagnetism. What is electromagnetism? The electricity and magnetism were united and become a single subject is called electromagnetism. When there is current, the magnetic field is produced and the current carrying conductor behaves like magnet. You may be now wonder how was impossible for a lodestone to behave like a magnet when there was no current passing through it. Only in the 20th century we understood that the magnetic properties arises due to the motions of electrons in the lodestones. In the circuits, the electrons flow from negative of the battery to positive of the battery and constitute currents. As a result, in produces magnetic field in natural magnetic and artificial magnetics that we buy in shops. The electrons move around the nucleus constitutes the current which leads magnetic properties. Here, every obtaining electrons in its orbit is like current carrying loop. Even though in all the materials electrons orbit around the nucleus, only for certain special type of materials called magnetic material, the motion of the electrons around the nucleus get added up. As a result, we have permanent magnetic field.